Sky Network member webinar. We're hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to welcome our guest speaker, Dr. Joseph DePasquale from the Space Telescope Science Institute. Before we introduce Joe, I'm not sure who it's going to be, Vivian or Kat, with just a few announcements.
With audio. Hi, everybody. Welcome to tonight's webinar. Just a couple of things to let you know. We just released a Celebrate Our Marvelous Moon poster just in time for the lunar eclipse coming up on the night of the 13th/14th. Oh, thanks, Brian, for sharing that. This is a sneak preview of it. If you are an active Night Sky Network club, you will automatically get a set of these sent to you so you can share them with folks for the eclipse. Hopefully you'll have some kind of fun event that night somewhere, even if it's just with your friends and family. We hope you have clear skies for that. So make sure your club is active and we'll just send that automatically. So what else? I think that's about it for now. And Kat, you got anything?
I do not,
Great.
but you can expect to see your monthly member updates on Monday of next week.
Handing it back to you, Brian.
All right, thank you. For all of you on Zoom, hopefully you found the chat window and the Q&A window at the bottom edge of the Zoom window. Please feel free to greet each other in the chat, making sure that you select everyone. You can also let us know in the chat if you're having any technical difficulties, or you can send us an email at nightskyinfo@astrosociety.org. If you have a question for our guest speaker, please type it into the Q&A window. It really helps us to keep track of things if you do that. So I'm going to go ahead and hit the record button here too. So again, welcome to the February NASA Night Sky Network webinar. Joe DePasquale is the Principal Science Visuals Developer in the Office of Public Outreach at the Space Telescope Science Institute in Baltimore, Maryland. Joe's work requires a unique blend of science and art to bring data from the Hubble and James Webb Space Telescopes to life in high-quality, colorful views of the cosmos. Before joining Space Telescope in 2017, Joe is the science imager for NASA's Chandra X-ray Observatory at the Smithsonian Astrophysical Observatory, where he worked for 16 years with our colleague Chanel Verani, who's with us here this evening as well. So his undergraduate training was at Villanova University. He has an extensive background in astronomy, art, and photography, and music, giving him a very unique skill set that's well suited to bringing observatory data to life with richly detailed imagery. Please welcome Dr. Joe Pasquale.
Thanks, Brian, for that introduction. I do have to say, though, I don't have my doctorate, so I am not Dr. DePasquale, but thank you for that.
We've given one you in absentia or something.
Yeah, an honorary title from the ASP. Go.
Yeah. Thank you. I accept. Okay, let me share my screen here. We'll get started. Okay, everyone can see the slides, right?
That's beautiful.
Great. Okay, thanks for joining, everyone. I'm really excited to be here tonight. I'm going to talk to you about revealing the invisible universe. Before I get started, I just wanted to give a shout out to my colleague, Elisa Pagan, who is my, here we go, yeah. Together, Elisa and I are responsible for producing most of the imagery that you see from the James Webb and Hubble Space Telescopes. Our European colleagues will work on images for European press releases, but otherwise that comes from us. So let's dive right in. Webb is a feat of engineering. It required several innovative and powerful new technologies to build Webb. Probably one of the most ambitious science experiments humanity's ever seen. And it has just been an incredible almost 3 years now seeing what Webb can do and what we're learning from Webb. Of course, Webb is an international collaboration, and I think this really demonstrates the, when NASA is most powerful, when we embrace the diverse skill sets and expertise of our international partners. It's a shining power of the power of that collaboration, shining example of the power of that collaboration. NASA headquarters, of course, oversees the mission for the agency's Science Mission Directorate. Goddard Space Flight Center in Greenbelt, Maryland manages Webb for the agency and oversees the work on the mission performed by the Space Telescope Sciences Institute, where I work, as well as other mission partners. STSCI, we conduct the science and mission operations from here in Baltimore, Maryland for Webb. And of course, as the lead agency, NASA has the overall responsibility for the Webb mission. So a little bit more about STSCI. We were founded in 1981 to support Hubble for the astronomical community. And in addition to being the Science and Operations Center for Webb, STSCI is also the Science Operations Center for Hubble and the soon-to-be-launched Roman Space Telescope. We started off with a staff of about 50 people back in 1981, and we've grown to over 800 employees with many areas of expertise. And of course, our vision is to expand the frontiers of space astronomy, and our mission is to help humanity explore the universe with advanced space telescopes and archives. A little bit about OPO, where I work, the Office of Public Outreach. As the Science Operations Center for both Webb and Hubble, OPO, it leads the news efforts for both observatories. And so that, of course, includes making the full color images that we produce for press releases, and you'll hear more about that tonight. Our vision within OPO is to make astronomy exciting, engaging, and understandable to relevant to a diverse audience. Connecting science and scientists to the public is one of our strengths. We have direct access to the scientists who are working with the data from the telescopes. And piloting emerging technologies to reach new audiences is one of our guiding principles. So let's talk a little bit about the electromagnetic spectrum. That, of course, Webb's specialization here is in infrared light. I love to talk about multi-wavelength astronomy. My career has kind of spanned multiple wavelengths of astronomy. I started out, as Brian said earlier, at the Chandra X-ray Center. So I was working with X-ray data. I kind of downshifted when I came to Space Telescope, working with optical data from the Hubble telescope, and now, of course, infrared from Webb. The Hubble Space Telescope is an optical telescope. It sees that sliver of visible light in the electromagnetic spectrum that our eyes are sensitive to. A little bit into the ultraviolet and a little bit into infrared, but its main area of focus is visible light. But of course, when we expand beyond the light that only our eyes can see, we learn so much more about the universe. And so Webb was designed to be somewhat overlap with Hubble in the near infrared and extend into the mid infrared, where it then overlaps with the now retired Spitzer Space Telescope, which retired in 2020. So just as an example of what we can achieve by observing the universe in multiple wavelengths, here's this beautiful image of the Crab Nebula. This was taken in 5 different wavelengths of light, spanning almost the entire electromagnetic spectrum. We'll start with the Very Large Array. This is the radio image contribution to this image. Here we're seeing, swirling electrons following magnetic fields within the nebula. If you're not familiar with the Crab, of course, this is a supernova remnant of a star that exploded in 1054, and we are seeing the aftermath of that explosion. And now we're seeing it in multiple wavelengths here. This is the Spitzer infrared view, which is tracing warm dust within the ejecta of the supernova remnant. And then kind of closely following that in optical light with Hubble, we see these fantastic tendrils from that ejecta material. As we move into higher energies and shorter wavelengths, we go to the XMM ultraviolet view. Of course, XMM is the X-ray multi-mirror mission. This is European Space Agency's X-ray telescope, but it also has an ultraviolet monitor telescope built on it as well. And so this is an image in ultraviolet light, which is now kind of peering into the heart of the Crab Nebula, the sort of radiation in the core there that is driven by the neutron star and pulsar, which shows up beautifully in the Chandra X-ray image here. Of course, that pulsar there, the beating heart of the Crab Nebula with a swirling torus of material all around it and jets coming out of either pole. And so that all comes together beautifully in this multi-wavelength image. And of course, I would be remiss if I didn't include, since we have observed this with Webb at this point, here's the Webb near-infrared view taken with Webb's NIRCam camera. So this is kind of pulling together a lot of that knowledge that we know from the multi-wavelength view and kind of focusing in on the infrared view. But we can see evidence of all that other stuff, right? We can see the torus. It kind of shows up as a little, these ripples within the blue glow of the nebula. So Webb is giving us a new insight into the universe. It's giving us, Hubble quality resolution at infrared wavelengths. And so with Webb, we can now peer through and examine dust in the universe. And that's not just the only thing it can do, but it's one of its strengths. Here we're looking at of course, the infamous pillars of creation. On the left is the famous Hubble image. In the middle there is the near-infrared image taken with Webb a few years ago. And you can see there that all of a sudden, this background of this tapestry of stars just shows through. That is Webb peering through the dust and taking that veil that is opaque in optical light and letting us see through it to see the background stars. We're also peering into the clouds that make up the pillars themselves here. We're seeing deep into them. We're seeing stars in the process of formation, these red glows. These are stars embedded within those clouds in the process of forming, with jets shooting out and heating up the material around them, glowing red in this image. And then to the right of that, we're looking at the mid-infrared image, which oddly enough, now that veil becomes opaque again, but we're now seeing the clouds themselves, the pillars glowing in infrared light. And where the pillars are most dense, they are almost black. So it kind of gives us insight into the composition of the pillars as well. Just a little insight into some recent news from Webb. This is an image of a light echo from a supernova remnant called Cassiopeia A. This is an observation taken in near-infrared light with Webb's NIRCam camera and was released in January at the Astronomical Society meeting. Light echoes are basically when a star explodes, there's a brilliant flash of light that spreads out in all directions, and if this happens to be in an area where there's material around it, there could be echoes of that light that, as that light propagates through the universe, it bounces off these materials and comes back to us. So this is the wide field view now. The background there is provided by the Spitzer Space Telescope, and we have a pullout showing Webb's view of Cassiopeia A on the left there. And then all the way over on the right side, we see this is where the light echoes were observed. Now this was actually taken, there were 3 observations taken about 6 weeks apart back in August to September of 2024. And so we can make a movie and see evolution of these light echoes over time, which is just fascinating to view. You think of this as like if you've ever been to a laser light show, when there's smoke in the room and the laser has like a beam that shoots out across your head, and you can see like the light is illuminating the smoke at different levels. That's kind of what we're seeing with a light echo here. All right, so I have a lot to get through, so I'm going to jump into the meat of this talk, which is to discuss the process of how these images are created, right? We start with the raw data from the telescope archives, then there's some intermediate processing that happens, and then we have the final image. Done. No, I'm kidding. Let's jump into how this is done. But before I do that, I wanted to give you an insight into, you've probably noticed that stars in Webb images have a very unique look to them. They have these 6 or 8 points to them, which is kind of one of the ways you can tell that an image is a Webb image and not a Hubble image. And that actually has to do with the optical system of the telescope. This here is an image of the mirrors themselves that was taken during commissioning, so back in 2022. This is actually from the NIRCam instrument. There's a lens in there that's specifically designed to take an image of the mirrors instead of what the mirrors are looking at, so that we can check the alignment of the mirrors. What you're seeing, the dark bars that run through are the supporting struts that hold up the secondary mirror. And then, of course, the 18 hexagonal mirrors that make up the primary mirror for Webb. Now, you'll see a lot of edges there, and edges in optical systems contribute to diffraction spikes or diffraction patterns. So every single edge, a perpendicular line will show up to a point source. And so every one of the mirrors, the 18 hexagonal mirrors, contributes this pattern to point sources or stars. And additionally, the supporting struts holding up the secondary mirror also contribute to the pattern that we see in Webb stars. It all comes together in the focal plane to create this pattern, and we see that in every bright star in a Webb image. All right. So why do we make these color images to begin with, right? I don't think I have to justify this to this crowd, but I will. Our main goal, of course, is to visualize the data. We have this amazing data set. Why not do everything we can with it to make it as beautiful as possible, to respect the data, to help promote science, to get people excited, to inspire the public. It illustrates the scientific discoveries, the concepts that scientists are working through with the data from the telescope. And of course, engaging the public is one of our main goals. And so where do we start with this? Well, acquiring the data, of course, would be the first place. We have an archive at Space Telescope called MAST. This is the Mikulski Archive for Space Telescopes. This is our main portal to access data from the Webb Space Telescope, from Hubble, and from many other observatories. MAST has an enormous archive there, and it's free to the public. Some data sets have a proprietary period of perhaps 6 months, but for the most part, the data are all available to anyone who wants to go in and learn about the archive and learn how to acquire the data. So we go through, look for an object, and you'll see what's available in the archive. You can pull down what you want. One thing that's really important to note is that the data we pull from the archive has already gone through some steps of processing. Our talented software engineers at Space Telescope have built a calibration pipeline that when observations are taken with Webb, it goes through this calibration pipeline and then is stored in the archive for download afterwards. And of course, you can always back out of that. If you're a scientist wanting to get to the most raw state possible of your data, you can always do that. And then you can rerun the archive yourself, or not the archive, you can rerun the pipeline processing yourself and tweak any parameters if you need to. But the starting point, of course, is fully calibrated data, ready, science ready. And that's where we start as image processors to build images like this one, the cosmic cliffs of Carina. And of course, I'm sure you've seen this one. This is a pretty famous image. But I want to step backwards, and we're going to look at the raw data for this, one of the images that went into making this. And so we'll start with this little corner up here. And even this is not the raw data. Let's go all the way back, right? As I said, you can go as far back as you want. This is what a single frame of that observation looks like. It has some interesting features to it. These are all well-known features of the detector itself that are fully calibrated, so we can basically subtract that from the image. The bright points you see here are the bright stars in the image. And it's important to note that this is the very first exposure and they're already saturated. And if you've seen raw data from the telescope, you may have noticed that some of the stars have these black holes in them. That's actually data from the core of the star that has been saturated, and we don't actually have valid data there. And so the pipeline processing will flag those pixels and set them to black. So we know that there's no data there. This is why that happens. Those stars have already saturated even in the first frame. Now, as I step through the next few slides, you'll see this is working through multiple frames, I believe 8 of them. And now we've gotten to the point where you have your first exposure that combines 8 frames together. And now you can see some hints of the nebula there. You can see the bright stars. Some of that noise and artifacts are still there, of course. That will be calibrated out in the next step. Boom, it's gone, right? The calibration pipeline knows about the artifacts that were in the data, pulls that out, and what we're left with is a really nice clean image showing the nebula and the stars. Now it does have some black spots sort of littered throughout. Those would be bad pixels or cosmic ray hits that happened during those exposures. That again can be calibrated out by taking multiple exposures and then combining them together, perhaps moving the camera slightly between each of those. So the next step is to apply this distortion correction and then remove those bad pixels through combining multiple exposures together. Now, of course, those things can all change over exposures, but the stars don't. So that's why the black holes remain in those stars. And this is just one single exposure in one filter, so one wavelength range within a much larger mosaic that makes up the cosmic cliffs of Carina. Now, I've already skipped over a bunch of processing steps just to get here, so let's go backwards a little bit, even more so. We're going to start with the process of what's called image stretching, and then I'll talk a little bit about how color is applied to the data to create the beautiful color images that we see. Image stretching refers to basically changing the pixel values in an image so that we can actually see what's in the image. The detectors on Webb, on Hubble, on most astronomical instruments, they have these really sensitive detectors that have a much wider range of sensitivity to light than our eyes do. And so when we open a raw image, basically it looks black, like what we're seeing here. On the right, we have a histogram, which shows us the distribution of pixels across the image. The way I like to think of a histogram, if you're not familiar with it, is if that image were to fall on the ground and all the pixels sort of spread out, and you wanted to put it back in some kind of orderly way, You could pick up a pixel and say, okay, this pixel is black, I'll put it in my black bin. This pixel is light gray, I'll put it in my light gray bin, and just build up, right, these bins of different pixels. That's essentially what a histogram is. And you'll see that in this histogram, it's very much bunched up in the black range of pixel values. As we go from the left to the right, we're going from black to white in grayscale values. But there's a lot of values because this is a 16-bit image. It has over 65,000 different values. So let's simplify things a little bit and look at a simpler image. This is what we would call a 2-bit image of a parrot. So there's really only 4 possible pixel values in this image. They're either black, dark gray, light gray, or white. And that's reflected here in the histogram. We've got our 4 bins of black, dark gray, light gray, and white. So stretching is the process of changing those pixel values in some way to bring out more information. With the parrot, of course, there's a lot of information. We already see most of what's there, but just as a demonstration, what I'm showing now is what we call a curves adjustment. This is not how we would stretch the data, but just as an illustrative example, this is what we would do. So on the left, there's no change here. There's, a diagonal line, slope of 1. Now we're pulling, in the middle, we're pulling the white point over to the left, right? So now we're taking white pixels, they stay white. The light gray pixels are now pure white, and those dark gray pixels are now pure white. And so we have essentially brightened the image, but we've lost information, right? We've washed out all the detail in the parrot, and we've basically just created a 2-color image at this point. So moving on to the right, this is what we call a nonlinear transformation. And this would be, some kind of function that would describe the curve that changes the values of the pixels. Basically just adjusting the midtones to brighten the image while preserving the details in the brightest regions of the image. So taking this back to our astronomical image, this is actually Webb's first deep field image of SMAX 0723. What I've done here is applied a linear stretch to the data, which does bring up a bunch of information. It shows us a lot of detail in the image, but it also has now saturated all the bright parts of the image. So the stars and the cores of the galaxies are completely saturated to white, and we've lost information. And that is reflected in the histogram, where you can see, a hard edge here to the white side of the histogram. If we apply a nonlinear stretch, we can preserve the data in the brightest regions and also raise the data, the pixel values in the darkest regions of the image so that we can actually see what's there. All of those faint distant galaxies are now visible to us just through the process of changing the pixel values. So the way that we would do this, one possible tool to do this is something called Fitz Liberator. You may be familiar with this. Fitz Liberator is a tool, a standalone tool that allows you to open a Fitz file. If I haven't mentioned this already, I apologize, but a Fitz file is the sort of the standard format for astronomical images. It stands for Flexible Image Transport System. When you download an image from the archive, it is a Fitz file. That's what you'll get. So Fitz Liberator allows you to open that Fitz file, see what's in there, adjust the pixel values, and then save it out in a format that's more friendly for image processing, say like a PNG file or a JPEG or a TIFF. So we would do that with multiple images to create a color image. So here we have the cosmic cliffs of Carina, though you may not be able to tell because it's very dark. It hasn't been stretched yet. The numbers underneath each of these images corresponds to a filter. And I'll get to what that means in a minute. Basically, it just corresponds to wavelengths of light. So we're going to stretch these now, and you'll see the cosmic cliffs come to life in multiple wavelengths of infrared light. Starting at the top left, this is 0.9 microns. This is just a wavelength, measuring the length of a wave of light in infrared wavelengths, starting in near infrared. So this is just beyond the red light that we can see with our eyes. And then we're stepping into longer and longer wavelengths as we move to the right and then down to the right. And this is where color comes in. So we've talked about image stretching. We're gonna get into what we call chromatic color. And I mentioned a second ago about the the filters on Webb. I have this this nice little demonstration movie here that shows you the light path through the MIRI instrument, which is Webb's mid-infrared imager. As light travels through the instrument, it is bounced off several mirrors, makes its way towards this filter wheel, which we'll see in a second here, right here. This is a physical mechanism on the telescope that allows the astronomers to put different filters into the field of view of the instrument to allow you to take images in different wavelengths of light. So those 6 images that we saw before, NIRCam has a similar setup where you have multiple filters and you can take images in all those filters. And that's where the color component comes in through the use of the electromagnetic spectrum again. Right, we were talking about this earlier. The light that we see with our eyes is a very small part of the electromagnetic spectrum, but we can use the way that our eyes respond to light to translate light from other wavelengths into something that we can perceive. So we're basically, with Webb, we're shifting this idea, right? Taking shortest wavelengths of light are blue, medium wavelengths are green, longest wavelengths are red. That's how our eyes perceive light. We have those cells in our eyes that can see that. It's the different combinations of blue, green, and red that make up all the colors that we see with our eyes. So if we take that same concept and just shift it while maintaining that relationship between shortest to longest wavelengths, we can then create color images basically in any range of light on the electromagnetic spectrum. Thinking back to the image of the Crab Nebula, we were seeing data from all the way to the radio, into infrared, into visible, to ultraviolet, to X-ray, covering almost this whole graph. And I used this same principle, I just spread it out across that whole range. So applying that concept to the images that we saw of the cosmic eclipse of Carina, we can now apply color in this chromatic order, where the shortest wavelength is blue, and as we move into longer and longer wavelengths, we're going to green and red. The F470N is a bit of an outlier here. Is okay because, well, I say it's okay, you have to trust me on this one, but the F470N is a narrowband filter that looks at a very specific wavelength range that actually maps to something that we would also see at 2 microns. And so for this image, we really wanted to highlight that one feature and have it stand out really well so that you could see it clearly. And so we used this this yellow color to have that pop out a little bit. And so it does follow the convention, the chromatic ordering of light. Of course, one of the other things we have to deal with these images is those image artifacts, which I was showing you earlier. A lot of them are calibrated out in the pipeline processing, but some of them make their way all the way through. Not everything gets calibrated out. So what we're seeing here, besides the black holes, the obvious black holes in the stars, there's also some striping. This we call this 1/f noise. This has to do with the way the detector reads data out. This is sometimes we see this in the shorter wavelengths of light, like the F090W image. That's something that we have algorithms to deal with. I wrote a tool that fixes the cores of stars, and so basically we can just erase all of those problems and make it sound really simple. It's not that simple. Sometimes it's actually really difficult, but we can get through it and then combine everything together to create what we would call the initial color composite. Excuse me for 1 second. Okay, so the initial color composite. This is where I like to feel, or I like to think of this whole process as kind of transitioning from a an analytic, quantitative realm into more of a aesthetic, qualitative realm. More like we can think about this more like a photographer at this point. We have the data there, and we want to color calibrate it. Actually, is one of the most important parts is color calibration. And so we're thinking about this in terms of aesthetic principles, clarity, tonality, right? Getting the colors right, and the composition, ultimately. These are important facts that aspects of the work that then take this image from its initial state into the final version that we would release for a press release. So with the cosmic eclipse, for example, if we were to present this to the public in the standard astronomical north up, east left orientation, this would actually be the orientation of the image, right? This is something that is a sort of a convention among astronomers, is to present things where north is always up and east is to the left, as if you're looking up from the Earth. That doesn't always work well as a presentation for composition of an image. And in particular with the cosmic eclipse, we wanted to give people a visual anchor. One of the big challenges with astronomical imagery is that you have no frame of reference for what these things are, what they look like. So anytime we can find something that gives you some kind of anchor to something that you're used to, that is a powerful visual element to help you become accustomed or acquainted with the object sort of initially, right? It guides your eyes in a way and helps you to feel at ease with what you're seeing. And so with the cosmic eclipse, I mean, even the name, right, suggests that this is like a mountain range. And oddly enough, some of the physical processes that are happening here are similar to what would happen in a mountain range. Just off the field of view of this image above here are some really bright, hot young stars with very strong stellar winds that are eroding the dense gas and dust just below, essentially the mountain range here. And that erosion is kind of sublimating. And so we're seeing this almost like mist rising up off the mountains. So it really kind of harkens back to something that you would be familiar with seeing on Earth. Now the color calibration steps come in here. Each of those filters has a certain response to light, and one may allow more light through than another one, and so color calibration is extremely important. It becomes difficult at times with infrared light because we don't have a lot of reference material for the colors in these wavelengths. You know, we're kind of, at least when we first started with this, we were applying concepts that we would use with Hubble, so optical light, to color calibrate infrared light. We've gotten a little better with this since then. But sometimes it feels like, you know, we're almost flying blind, and there is sort of, and it's more about aesthetics at this point, but we definitely want to make sure that the colors are right? The stars have certain colors, depending on their temperature, and that needs to be reflected in the image, and the process needs to respect the data, of course. We can't introduce things that weren't there already, and we can't change things just sort of randomly to suit the needs of the image. As I'm stepping through here, we're seeing multiple iterations of pulling this image together. Now, this was one of Webb's first images, and so this was part of the early release observations, or EROs. For this set of images, we had a team of scientists, designers, image processors, myself and Elisa. We all worked together. We consulted with scientists on the exact orientation, the look of these images to make sure that what we were presenting was accurate and would help to tell the story of the data. And so this was actually an example of taking things a little bit too far. The color saturation was just a little bit much here, and so we backed off of that a little bit and focused a little more on trying to bring out details within the mountain range itself. We wanted to show the mist rising off the mountains. You know, I can't help but go back to that analogy of the mountain range. It's so natural to me now. Other things in this image, remember I mentioned the yellow feature in that one filter. That's actually something we can see here. These, if you're seeing my mouse, I think you are. There's a bright star embedded in this cloud with jets shooting out of both poles, and those jets are plowing into the dense gas and dust of the material around it and creating these bow shocks. And you can see that very clearly here. And that was kind of the goal of using that yellow for that one particular filter. And then here, of course, is the final image. All right, so a question that I often get, and I hopefully don't have to convince you all that these are real, but is this real, right? Is this what it would look like if I could somehow go there? I like to, when I talk about this, I always like to bring it back to Earth and talk about, like, have you ever been to a dark sky location and seen the Milky Way? I've taken pictures of it. This is actually an example of pictures that I've taken at Shenandoah National Park a few years ago. The image on the left, if you can see this, is a 5-second exposure of that scene that kind of captures what I remember it looking like to my eyes. Right, our eyes are really good for the environment that we find ourselves in for the most part, which is you know, a daylit sky lighted by the brilliant light of the sun. And so they're very good at seeing in that kind of environment. But when the sun goes down and it gets really dark, the rod cells kick in, and our eyes see in less detail, less clarity, and less color in dark situations. We're not really designed to be, you know, telescopes for our eyes. We can't integrate light like a telescope can, or a camera in this case. So the image on the right is a stack of like 5-second exposures, or maybe actually it's 20, I think, in this case. And so that allows you to pull out so much more detail in the faintest regions of this image, right? We can see the dust lanes of the Milky Way here. We can see the bright core of the Milky Way shining brilliantly. We can even see the green of the trees in the foreground and the faint blue of the mountain range behind. All of this was never visible to my eyes in that scene. That doesn't make it any less real. This is just using technology, using instruments that we built to extend our capabilities to see things that we can't see. I also like to make this analogy to clouds when we're talking about nebulas like the cosmic cliffs. The reason they have the appearance they do is partly because of the distance, right? The distance is involved. Cosmic cliffs of Carina is like over 7,000 light years away. That amount of distance between us and it gives it a certain perspective and almost makes it have this, give us this perspective of it being a mountain range, when in reality, it's essentially empty space, right? If we were to actually fly out there and move towards the Carina Nebula, that would be just essentially just an empty area. You wouldn't see anything, right? It's the distance to it. So if you're, on the ground looking at a cloud, it can look like a solid object. But when you fly up in the sky in a plane, flying through the clouds, it's a very different experience, right? Of course, they're not solid. It's just water vapor. So moving from astronomical, let's move down to the world of the impossibly small. We see scanning electron microscope images of the coronavirus particle, and we know that that's a real object. We can't see that with our eyes, of course, but we've built microscopes to allow us to see the world of the impossibly tiny. And then we can take that data and extrapolate on it and build visualizations like this one on the right from the CDC of the coronavirus particle that is color-coded to give us some insight into the proteins on the particle. Now, it's no different with a telescope. We're seeing real objects with an instrument that was designed to look for that kind of object. This is an image of the Southern Ring Nebula that was taken with Webb for the early release observations. On the left, of course, is the black and white, that's real image. On the right, it's also a real image, as opposed to what we were just looking at with the coronavirus particle, where the image on the right was actually a visualization based on data. I would argue that the image on the right here is the real data. It has just been combined together in color to give us new insight into the object itself. And now I'd like to transition a little bit into some of the more sort of connections between art and astronomy, using Tarantula Nebula 30 Doradus as an example. This is an image that has a nice home in my heart. It was the first data that we got from Webb for the early release observations. I remember this was during the pandemic, of course. I was sitting right here at my desk in my basement in my studio and working on this image. And at that point, we knew that Webb was operating to full capacity, was making some really great images just from test data, right? In single wavelengths, we didn't have any color images yet, but we knew that the stars were sharp. We had an image that showed a background full of galaxies in a single wavelength. So we knew we had a functional observatory, but we didn't quite know, and we never really did until we got to this point, whether or not the colors would pop the way they do with the Hubble image. And this was my first foray into seeing how a full color image from Webb would actually come together. And it was a spectacular experience, a very moving experience. And so what we're seeing with Tarantula Nebula is a cluster of hot young stars right in the center there, that blue region. This is a cluster of stars that is blowing, with its stellar winds, blowing a big bubble, this area here, this cavity, through a region that is filled with gas and dust. The universe is just filled with gas and dust, right? And so there's always this interaction between gas and dust and stars that gives us these amazing views. Here is the ERO's team looking at like the very first frames of that image coming down from the telescope. This was really an exciting time to be on the Webb team, to see the first real observations coming down. And here's where I like to make this connection. When this image was first released, it was compared to sort of Renaissance paintings, old masters style painting, right? So I did some digging and I found this this painting from Caravaggio, Judith beheading Holofernes. Now, despite the macabre nature of the painting, I really felt like the colors, the tonality, even the arrangement of the figures really echoes what I see in the Tarantula Nebula here. Now, as I was saying with Tarantula, we have, of course, observed with multiple filters to get those colors, right? And so here's the NIRCam full suite of filters. This image is made up of 6 of those, or actually, I'm sorry, 4, spanning these wavelength ranges. So, near infrared into getting into mid-infrared at 4 microns. Here are the individual images themselves, and then with the colors applied using the chromatic ordering. and then we get the full color image from that. There were some really interesting issues with this particular image. Early on, we didn't have full calibration yet of the instruments of the cameras, and so we had some optical distortions that we had to deal with that had not yet been calibrated out of the system. And so this image in particular had stars that when we combined the color images together, they didn't quite align correctly. And because we didn't have the time, or the software engineers had not yet accurately calibrated what this issue was, I was basically forced to go in by hand and fix this. So I had to use a warp tool to adjust the positions of stars kind of somewhat arbitrarily, just to make sure that they would all overlap to create the color image where the stars are fully overlapping. Another interesting feature of this image is that one of the filters used is a medium band filter, and we experimented with a technique called continuum subtraction to use that filter to really hone in on a very specific wavelength of light. So the F335M is looking at very specific wavelength here. It's isolating polycyclic aromatic hydrocarbons, basically soot in space, and so this is like warm dust that's glowing from the heat of the stars around it. And to get to the continuum subtraction image, we had to use that 2 micron image, basically subtract the 2 micron from the 3.35 to get an image that just really focuses in on those PAH values. And so the analogy I like to make is, imagine we take this painting from Caravaggio and break it down into its color channels, and then focus in on just the red image, right? And say, okay, well, yes, the red is shining here very clearly, like that tarp in the background is bright, so I know that it's red. But what if I just wanted to focus in on the color of blood? Right, so we can do that. It's kind of like what continuum subtraction is doing. All right, so let's go back to the color combination here, and I'm going to start by just combining in. We're going to ignore that narrowband image and just use 3 images here to create a 3-color image in red, green, and blue. And so this would be the initial color composite, right, for the 30 Doradus image, Tarantula Nebula. This needs color calibration, and again, this was one of those situations where there wasn't a lot of frame of reference for how to color calibrate it yet, so it's kind of just figuring it out as we went. Here is overcompensating for red. Now I'm looking towards suppressing the red a little bit, bringing out some more detail within the cloud structure itself. Again, dealing with the reds, I wanted to find a balance between the red shroud of gas and dust surrounding the cluster of blue stars. I still didn't see the blue stars shining through. So now I'm focusing in on really getting details within the clouds and allowing the stars in the cluster to shine through. Here it's been overdone a little bit, so we have to bring some of that color back. And so as I'm stepping through this, I am showing you the process from start to finish, each iterative step of getting from that initial color composite to the final version. Now this next one is actually going to be where the 3.35 micron PAH image comes in, and you'll see the red clouds kind of pop to life. That really brings out the details of those particular features when we bring that in. So I'm blinking back and forth between them. And then one last time, come back to the Caravaggio painting, and seeing them side by side, I always marvel at just how eerily similar these two are. It's really interesting to me. All right, so another example of where art and science came together was going back to the cosmic eclipse of Carina. We actually observed this with, so this image is of course NIRCam. We also observed this with the mid-infrared instrument, the MIRI instrument. And that was this image. Now MIRI has a smaller field of view, so that's why we didn't get the full coverage of the entire image, but we did focus in on this region here. And this is actually an image that combines MIRI with NIRCam, right? In this sort of color arrangement, or no, I'm sorry, this is not the color arrangement. This was what I would normally think of to create a color image from NIRCam and MIRI is to start with the shortest wavelength light in blue and then move my way through green, yellow, orange, and red to get to a full color image. And when I did that with the MIRI data, we ended up with this image, which concerned me, to say the least. The colors are really strange. It looks very foreign. One of the interesting features here is that, when we saw the image of the Pillars of Creation early on in this talk, you saw how in NIRCam, those stars in the background just popped out, right? Popped out of that veil that they're opaque in optical light. But then as you go into mid-infrared, it becomes opaque again. And so we have that same situation here where the stars are showing through in the NIRCam wavelengths, but then when we get to MIRI, they're just completely gone. And so if I assign those stars just from NIRCam the blue colors, you end up getting just purely blue stars, which is a very unnatural look to an image like this. And so I gave this some thought. I thought, why don't I focus in on just what the MIRI data looks like by itself? And I created this image. So this is now a chromatically colored image of the same region using just the MIRI data, mid-infrared data. And so this actually, I saw this and I thought this is like a completely different view of the same object. This looks like, if we were seeing the cosmic cliffs in midday earlier, now we're looking at them at dusk or something like that. And so it actually caused me to think of Rouen's paintings, Claude Monet's paintings of the Rouen Cathedral in France. He captured this same scene multiple times, like 30 times or something, really trying to focus in on the atmosphere of the scene, the quality of the light, depending on the time of day that he was painting it. Whether it's a warm light from a setting sun or a rising sun, or if it's the harsh light of an afternoon sun, he wanted to capture the atmosphere of the scene and not just like a picture of it, just the feel of it. And so I came back to the NIRCam and the MIRI data, and I thought, well, what if we tried combining the best of both worlds? What if we took the NIRCam image and the MIRI image and sort of interleave the wavelength ranges of both cameras? So we take the shortest wavelengths of NIRCam and MIRI and then assign those blue and then move through to the green and the red. Well, that's how we got to this image here of the cosmic cliffs. So this now brings you to an image that still preserves some scientific information. That bright star with the jets shooting out of it is showing off really well here. It's deeply embedded, so it's a very red star, and that shows off extremely well when we do this, when we apply this method. It has the added benefit that all the stars have this natural look to them. They have bright white cores, but their colors are accurate and shine through as well. And it gives us just a new perspective on this whole region of the Carina Nebula. And so with that, I would happily take questions, and I thank you for your time.
That was fantastic, Joe. I have to agree with you. Seeing the Caravaggio painting and then the Tarantula Nebula side by side when you showed that mosaic, if you kind of use averted vision, the tonality, the composition, the colors, it's eerily striking how similar they are. It did strike me. We have a lot of questions from our participants. So let me bring up our Q&A window. And as I'm getting oriented, I thought I'd take the purview and the opportunity to ask you the first question. That is, do you remember what was the first cosmic source, that Webb image that you saw come down from the telescope? And then what you thought of just the raw data compared to all that work and all that effort and just getting the telescope up and on sky?
Yeah, I have to say that the first, like I said earlier, the first color image that I saw was the Tarantula Nebula, this one here. Mm-hmm. So that was my first exposure to what a full, beautiful color image from Webb could look like. And it was the moment where I was like, yes, this is as good, if not better, than what Hubble could produce. And I can't believe that I get to make this image right now.
Right.
Before that, it was I forget which source it was, but we had a bright star that we used to test the alignment of the mirrors. And so that was like the first real cosmic source where we could see like a bright star, but also beyond the bright star is just a field of galaxies.
Right.
Yeah, like that was one of the things we noticed with Webb is like no matter what you look at, you get the object that you're interested in, and then you also get a deep field every time. It's beautiful.
Right.
Yeah.
So that actually is a question that John asked, and it had to do with exposure. And I guess there's two parts to that. Of course, the exposure on a given target, that could range from target to target to get the science done. But is there like a minimum frame time exposure, like with a CCD camera of 3 seconds that you're building up, or what is the exposure, the minimum exposure you can do?
The minimum exposure, I mean, I think it's like fractions of a second is a minimum. We've observed Jupiter with Webb, and Jupiter, of course, is extremely bright and actually doesn't even fit within the detector. And you actually have to take multiple images and then stitch them together, right? And they all have to be very fast exposures because of how bright it is, or else it'll saturate the detector. So Webb is able to produce an image of Jupiter as well as an image of, deep field, looking at it for many thousands of seconds kinds of images.
And then a question from Jeff, for a lot of our astronomers on the call, of course, they have their own setup, their own telescopes and detectors. And of course, we'll do a very similar version to the kind of data production workflow that you have. But what is the calibration, the pipeline calibration that maybe is unique and specific to space telescopes that a typical observer won't maybe do? The question is, what is the calibration and early processing? And I think that's what he's trying to get at.
Yeah, so a lot of that is actually what an amateur astronomer would do. It's taking your bias frames, your dark frames, your light frames, integrating all that together, cleaning up the data as best as possible to create your like science-ready frames. So it's very much the same process. It's just tailored to the specific observatory.
Okay. And then Chris asks, is there, he says there's a standard Hubble color palette for Hubble photos. Is there a similar analog for James Webb?
Yeah, the question of color palettes is interesting to me. I think the Hubble color palette came out of doing narrowband imagery with Hubble, where instead of coloring, say you were going to take an image in sulfur, hydrogen, oxygen, right? Sulfur and hydrogen are both in the red portion of the spectrum optically, and oxygen is like teal. And so if you make an image in the colors where they sit in the spectrum, you get a very red image. When the Pillars of Creation's image was created, the very first one with Pic 2 from Hubble, the image processor decided to basically what I was talking about earlier, like spreading out the colors, the color space that you have available. Instead of assigning them the colors that they sit at in the spectrum, open that up and say, okay, take the shortest wavelength, take the oxygen light and color that pure blue, and then take sulfur and give that green, and hydrogen is red, and then you get this like a much wider color gamut to work within that is actually, I would think, more informative as an image. And so we use that same mentality for Webb as well. Unfortunately, you can't say that like any given image is going to have the same exact color mapping for each filter, right? Because it really depends on what filters are available for that particular data set. And so a lot of the examples I showed, you saw like the F090 was blue. And that probably will be true in most images if it's just Webb data. But if we're combining data from Hubble and Webb, then that F090 filter may end up being green or red, depending on how long its wavelength is compared to everything else. And
then a question from Rick on your workflow. The imaging processing software that you use, is that custom? Is that like DS9 astronomy specific? And then where does Adobe and those kind of other vendor software, GIMP is another example, where do they fit into your pipeline, into your workflow?
Yeah, that's a great question. So I actually am very partial to PixInsight, and I should say that I'm not endorsing any particular products here. I'm just speaking about my workflow. So PixInsight is like Photoshop developed by amateur astronomers for astrophotography, right? It has a lot of really powerful tools specifically for astrophotography. And I really like it for combining data together to create a color image, and really, really like it for color calibration. They've just recently incorporated the Gaia catalog into PixInsight in a tool called spectrophotometric color calibration, which whenever I'm working with Hubble data, I try to use that to get my color calibration as accurate as possible. It's not always possible because Hubble's field of view is so narrow compared to, an all-sky survey. You may not have enough stars in the image to do that kind of calibration, but whenever I can, I do. And I use that to inform color calibration in other images as well. For Webb, I was saying early on, it was kind of hard to get the color calibration right. But something like a deep field image that has galaxies in it is really useful for color calibration, because I end up using any kind of face-on spiral galaxy that I can find in the image as a white reference when I'm doing color calibration, and that is hugely beneficial for getting a really nice balanced color image. And so I should say, my workflow continues from PixInsight. That's where I do my initial color composite. I then pull it out of PixInsight and bring it into Photoshop, where I do more of the fine-tuning and adjustments and compositional changes.
I have to say that, in that chat discussion, Luke, one of our participants, quickly responded saying that, oh, that looks like PixInsight. So I'm not sure how they were able to tell, but they called it right away.
Oh, yeah. Yeah, I think there's one slide in here where I have PixInsight windows or something. Yeah.
Oh, yeah, okay. That makes sense. I'm going to merge these two questions because I thought they have a very similar theme. Tony is more of a comment that he appreciated the workflow, and that to him, the perspective you bring is that of an artist trying to tell a science story. And that was just a comment that being able to bring the artistic side to a science endeavor is a real skill in that way. And then to follow up on that, Kirk asks, how long? And I suppose there's no typical answer, right? Some will take a long time, some maybe much longer. But what's a reasonable amount of time you would spend, like, say, on an image? How much did you spend on the Tarantula Nebula? It probably took a lot of time.
Yeah, Tarantula probably took about a week to get completely done from start to finish. But that was during a time, the EROs was just an incredibly compressed time frame to get everything done. We had 6 weeks from the first observations to the release of those images. And so we had to get everything, get all the data, get it all processed, get it calibrated, pulled into color images, pull the packages together, and put out the press release in 6 weeks. So that was intense. Normally, we don't have that kind of pressure to make an image, and so I'll take some time with things. Sometimes I'll do an image 2 or 3 times before I get it where I want it. And I mean, when I say 2 or 3 times, I start over completely from scratch. I feel like that's, for me, the only way I can really get it from the raw data into the final version.
Okay. Yeah, we're getting close to the top. So maybe just one more to come back to that workflow and the time it takes. Of course, given the labor and the skill you bring, that can't be done for every single image that comes down from Webb, right? So is there a process or a procedure that the outreach team uses to know, that's going to make for a compelling visual to produce for the public? Can you talk a little bit more about, how do you choose what data sets to put that labor and intensity into?
Yeah, so that's a great question. I would say there's like a two-pronged approach to that. One prong is that we are a news office, right? So we're helping scientists to promote their findings. And so scientists will observe with Webb, they'll produce their papers, they'll have their results, they'll come to us and say, hey, we think this is a newsworthy result. Would you like to do a press release about it? And so we have a team of scientists who will evaluate that and determine whether or not we should follow through with doing a press release. If we choose to, it then comes to Elise and I, and we will do the best we can with the data available to make an image for the press release. That doesn't always produce the most compelling images because we're just working with science data at that point, right? It wasn't designed to make a beautiful image. Sometimes it does, sometimes it doesn't. I think it's all beautiful, but sometimes it's just like a red dot, and that's the whole point of the story. The other side of that is that we have a team within OPO, we call the Outreach Imaging Team, which I'm a part of, where we actually look for compelling targets that we know we're going to make beautiful images, and then we will, like the astronomical community, we will request time with the observatory through the director's office to use the observatory to create a beautiful image for a press release. And then, we design the observations so that they're useful for science data as well. And so people can do real science with that in addition to having this beautiful image. So any kind of like anniversary image that we put out, that comes under the guise of the outreach imaging team.
Thank you, Joe. That was fantastic. Before I turn it over to Brian, I just wanted to echo something you mentioned earlier, that all the data, of course, is in the archive, the MAST archive. And if we haven't put a link, we'll put a link in the chat. But right, the public is invited to download and to look at the data. And of course, the images you make, they're public domain in the sense that they can use them in their presentations, both of their clubs or in any outreach and community event outreach events, correct?
Absolutely. It's the people's data. You can get it from webtelescope.org or nasa.gov.
Thank you, Joe.
You're
Brian?
welcome. Thank you.
All right. Well, that's fantastic. So a couple of things here at the end. I put in a link to the Cosmic Conversation, which we'll have next week. And so the link to register for that is live, and it's in the chat. And we hope to see a lot of you there next week. We also have the survey, and so maybe I could get Kat to put the thank you very much, Kat. You did it right when I mentioned it. So fantastic. So that's all for tonight. And so do join us next week for the edition of Cosmic Conversations. That's Tuesday, March 4th at 5 p.m. Pacific. Our next webinar is only a week later. It's only 2 weeks from now. It's on Tuesday, March 11th, when we welcome Dr. Burcu Kosar, who will tell us all about sprites and how you can get involved in their study. And so we also want to thank Joe for joining us this evening, and thank you everyone for tuning in. You can find this webinar along with many others on the Night Sky Network YouTube channel, and so keep looking up. We'll see you next week for Cosmic Conversations, and in 2 weeks for the next webinar. And please fill out the survey and remember the registration link for Cosmic Conversations. So, and that's it for this evening. So thank you very much, everyone.
Thank you so much.
There we
And, Joe, sometime in the next couple of days, we will put together the numbers of how many people we had. I think that the most I saw that were here were about 198, and then Kat had something like 150 on YouTube. So we were very well attended. And so I'll get the final numbers and a little bit of survey data to you within the next couple of days. I